Okay, let's jump right into this explainer. Today we're exploring the absolutely fascinating world of copper 2 sulfate. Now, this is a compound that seamlessly bridges heavy industrial chemistry with breathtaking contemporary art. It's a substance that has quite literally shaped our world, from the food we grow to the art we create. And it all starts right down at the atomic level. But before we get into the heavy science and those massive industrial applications, I want to pose a really intriguing question for you to keep in the back of your mind. Why does a single compound have such a dramatic split personality when it comes to color? I mean, how can the exact same fundamental building blocks look so completely different? Well, we are going to solve that mystery shortly. So here is our roadmap for today. We'll start with Section 1, the magic of bluestone, then move into 2, the chemistry of color, explore 3, preparation and reactions, see its real-world impact in 4, from farms to fine art, and finally cover 5, toxicity and safety. All right, let's start with Section 1, the magic of bluestone, and look at the basic identity of what we're actually dealing with here. Throughout history, humans have been totally captivated by this inorganic salt. It's generated by reacting sulfuric acid with copper, and it has gone by some pretty highly descriptive names over the centuries. You might see it referred to as blue vitriol, Roman vitriol, the vitriol of copper, or simply just bluestone. And most of these historical names highlight its striking appearance, right? Which has made it stand out to chemists and artisans alike for generations. Now, the physical contrast between its two forms is incredible. In its dry and hydrous form, it's basically just a white powder sitting at a density of 3.6 grams per cubic centimeter. But when it becomes a pentahydrate, meaning it binds with 5 water molecules, it completely transforms into those intense blue crystals we usually associate with it. Notice how the molar mass jumps from 159.6 up to 249.68 grams per mole, and the density actually drops to 2.286 grams per cubic centimeter. It is a completely different physical profile. Moving right along to Section 2, the chemistry of color. Let's solve that mystery I posed at the very beginning of the explainer. So the secret to this wild transformation lies in something called an aqua complex. When the white anhydrous copper sulfate encounters water, it exothermically dissolves, meaning it releases this little burst of heat. The water molecules basically act as ligands, which just means they surround and bind to the central copper ion. And this completely transforms the molecular geometry of the copper into a distinct octahedral shape. If you picture it, it looks a bit like 2 pyramids stuck base to base. And this brilliantly illustrates the exact mechanism behind the color change. When those water ligands surround the central copper metal, they cause what chemists call a d-d transition. Now, that's just the movement of electrons between the d orbitals in the transition metal. This specific shift in electrons emits light right in the visible region. Because of the specific energy of this transition in hydrated copper sulfate, it emits that famous intense blue color we can see with our own eyes. No water, no d-d transition, no blue color. It's really that simple and honestly, that elegant. Let's move to Section 3, preparation and reactions, to see how this builds from raw materials into a highly reactive chemical powerhouse. Now, heavily drawing on the preparation of copper sulfate crystals presented by Dr. Chem, if you want to make these yourself, there's a beautifully straightforward industrial process. Step 1, you treat metallic copper with heated concentrated sulfuric acid. Alternatively, you can treat copper oxides with dilute sulfuric acid. Step 2 is to simply crystallize the compound from the solution to produce that blue pentahydrate form. And here's a great quick note from Dr. Chem's presentation for those of you in a lab setting. When you're measuring the mass of the copper sulfate pentahydrate produced, using a highly precise mass balance can greatly reduce your measurement uncertainty. It lowers the absolute uncertainty of your final yield calculations, which, as we know, is absolutely crucial for good chemistry. So a super crucial point here is that copper sulfate is incredibly reactive, specifically in single metal replacement reactions. If you drop zinc into a copper sulfate solution, the zinc actively takes the sulfate, leaving behind metallic copper. The exact same dynamic swap happens with iron. Submerge a piece of iron, and it instantly swaps places to form iron sulfate and pure copper. Because it's so eager to absorb electrons and form metallic copper, it makes a perfectly reliable cathode solution or electrolyte for galvanic cells. Literally an absolute staple in high school chemistry labs everywhere. Another reason it's so beloved in education is for demonstrating mineral hydration. Because this is a reversible reaction, you can just take the blue pentahydrate crystals and heat them up to evaporate the water. It naturally loses 2 water molecules at 63 degrees Celsius, 2 more right around 109 degrees, and then that final stubborn molecule at 200 degrees. What you're left with is the white anhydrous powder. Add water back in, and boom, it instantly turns blue again while releasing heat. It is just the perfect visual tool for teaching both mineral hydration and exothermic reactions. All right, for section 4, from farms to fine art, let's zoom out to the macro level and look at its surprisingly diverse applications out in the real world. The sheer utility of this compound is staggering. In agriculture, it's mixed with calcium hydroxide to create Bordeaux mixture, protecting grapes and berries from fungus. In water management, it's one of the most effective treatments for controlling algae in lakes and clearing out invasive zebra mussels from water pipes. In the medical and analytical fields, it's used in Failings and Benedict's solutions to test for reducing sugars. Historically, it was even used to test the specific gravity of blood to check for anemia. Basically, blood with enough hemoglobin sinks in the solution, while anemic blood floats. And believe it or not, industrially, it's used in Schweitzer's reagent to dissolve cellulose for the production of rayon fabric. Just incredible versatility. But hey, its uses aren't all strictly business or science. It has a profound place in the art world, too. Printmakers have long used it to safely etch designs into zinc and copper plates for intaglio printmaking. But perhaps the most mind-bending application happened in 2008. Artist Roger Hjorns took an abandoned waterproofed council flat in London and pumped in 75,000 liters of copper-2 sulfate solution. He left it for several weeks to crystallize, and when he drained it, he'd created a piece called Seizure, an entire apartment where the walls, floors, and ceilings were completely covered in massive, immersive blue crystals. It was literally a sprawling, man-made crystal cave right in the middle of London. Now, as beautiful as that crystal cave is, it leads us directly into our final section, Section 5, Toxicity and Safety, because we absolutely must address the serious safety precautions required when handling this visually stunning but hazardous compound. An LD50 of 300 milligrams per kilogram is the median lethal dose for rats when taken orally. While copper sulfate was actually used in the past as a medical emetic, meaning it was given to patients to intentionally induce vomiting, well, it's now considered far too toxic for that purpose by modern medical standards. So yeah, definitely don't try that at home. Furthermore, 100 milligrams per cubic meter represents the immediately dangerous to life or health limit for copper sulfate exposure in the air. This highlights exactly why proper industrial handling, proper ventilation, and wearing your protective gear are so strictly regulated when manufacturing or applying this chemical. So, if you're working with this material, you must be extremely cautious and follow the globally harmonized system labeling. It is harmful if swallowed and causes serious eye damage. But perhaps most importantly for its environmental use, it is catastrophic and highly toxic to aquatic life, specifically fish with long-lasting effects. This makes its use as an algae killer a very, very delicate balancing act. Additionally, while it can emit a brilliant green or blue light in flames, you must never mix it with metal powders or chlorates in fireworks. Doing so poses a highly dangerous explosive hazard. As we wrap up this explainer, I'll leave you with this provocative thought. We've seen how this compound can protect our food supply, test our blood, and even inspire breathtaking art. But we also know its severe toxicity to aquatic life and to ourselves if it's mishandled. So how do we continue to harness the incredible chemical power of this dual-natured compound without harming the delicate ecosystems of the world around us? It's a chemical tightrope we're going to be walking for decades to come. Thank you so much for joining me today, and keep questioning the science all around you.